If you have been here before, I think you already know Michael. When you think about Austrian people, you expect something very serious with no sense of humor. And I think that Michael is just the opposite. So I think almost all his talks are something like having fun with whatever. So this is no exception. You should have one of having fun with exceptions, by the way.
This isn't as funny as the last one. I thought I should tone it down a bit after what happened last year.
Come on.
It would have been hard to get funnier than last year, though, right? So I had to course correct.
Okay, Michael, thank you very much for coming again. And the floor is yours. Thank you.
Thank you. So it's still early in the morning, at least for me. So let's start with a little bit of action. Who here has heard about coroutines in C++? Okay, that's maybe half the people. Okay, that's concerning. Who here has used C++ coroutines? Half the people who have heard about them. Okay. Last action. Who here has written a custom coroutine type? And we are down to six people, I think. Okay, this will be something new then. So let's start with a few statements and continue with the action. Who here thinks coroutines allow you to do something that's not been possible before? 1 hand, 2 hands, 3 hands. Okay, people are not sure. Who thinks coroutines about async code? More hands. Well, you get the impression from pretty much all the talks about coroutines we've seen in the past. So let me push back a bit about these two statements. Coroutines don't allow you to do anything that wouldn't have been possible before. The amount of code you'd have to write to do something like coroutines may have prevented you from doing so, but they don't enable any new code per se. And they're not about async code. They're synchronous in nature. They fit certain models of concurrency quite well, but they are not asynchronous at all. And let's start with the basics. So we talk about coroutines as if they are something new, but if you look at where they come from, they are more than 60 years old at this point, because they were invented in '58 by Melvin Conway. He published a paper about it 5 years later, and I think it was about the optimization of a COBOL compiler, where we have a similar model to C++ with multiple translation phases. But back in the day, that meant I have a tape, I load it through one phase, I get the tape with the computed translation, and I put the tape back again to start the next translation phase. So with his optimization, it was possible to do that in one step. In '65, the first Simula 1 compiler was released. And we always point to Simula as this language we borrowed our concept of object orientation from. The funny thing is, according to the data I've seen, the first version of Simula didn't have object orientation. It did have coroutines though. 3 years later, we get to Simula 68, which is the one we took object orientation from. In '72, there was C. Obviously, it didn't have coroutines back then. It doesn't have now. In '79, we got C with classes. And if you read D&D, there's an interesting statement in there where the first serious library written with it was a task system, which relied on object orientation from what I gather, because there was no language feature back then for coroutines, right? Yeah, sure, it was a library. It was not a dedicated language feature. Oh, that's interesting. Unfortunately, that library was not standardized. So in '98, we got the first C++ standard, and it had no support for coroutines. And it stayed that way for quite a long time. And if you weren't in the committee like I wasn't back then, the first time you heard about coroutines in C++ was probably in 17, when this thing, the coroutine TS, was announced, released. Well, 3 years later, that stuff was merged into C++ 20. But what is a coroutine? And to answer that, we first need to talk about what is a function. Because if you look at it at an abstract level, a function has two abstract operations. One of them is we can call another function, in which case we suspend the current function we're in and activate another function that takes control of the computer. At some point later, the second action takes place, which is return, which cancels the function we are currently in and yields some value back to the caller. And I'm using yield here very loosely. That includes throwing an exception or returning nothing. So what is a coroutine? Well, it's something that has the same two basic operations and adds a third. It is still callable like a function. It can return, but it can also suspend. And when it suspends the current function and yields a value back to the caller. But at a later point, you can call it again, and we call it resume. And it will continue running from where we left off. And we can do this an arbitrary number of times until we reach a return. So how do we actually implement something like that? And there are essentially two ways to do this. They are called stackful and stackless. The stackless approach is something that looks like a function, it's executed like a normal function, but its local state is not in the call stack that includes all its inputs, all the temporaries you need, all the local objects. All that lives in something that's called the coroutine frame, which is some area of memory we associate with the state of the coroutine. For comparison, a stackful coroutine is more akin to a thread. It's scheduled onto a kernel thread, and it keeps running. All its state is just on a stack because it's like a thread. So, stackless coroutine has a serious limitation. They can only suspend directly in the body. So you can't have a stackless coroutine, have it call another function, and in there say, well, I now want to suspend and be continued from here on later. That does work for a stackful coroutine. So you can have an arbitrarily nested function call, and at any point then say, well, I need to stop now and hand some over to somebody else. Stackless coroutines need language support because there's extensive transformations going on there. Because the code you're writing is not looking at all like the code that's going to be executed. Contrast that to stackful coroutines, which can actually be implemented as a library. For example, Boost has, I have lost track of how many they actually have. They all depend on some low-level context switching library, but there's coroutine 1, coroutine 2. There's a fiber library, and yeah, obviously you can implement this rather easily. In C++ 20, coroutines are stackless, and we have 3 new keywords with this nice co-prefix. That doesn't mean stackful coroutines aren't interesting. And there's actually a paper going through Library Evolution that's going to standardize stackful coroutines in the form of fiber context. The idea being this being the low-level framework you can then build upon your custom fiber type. So what's the most trivial coroutine we can write in C++? It looks something like this. So it looks like a function, and it does one co-return and nothing else. There's some things to unpack here. First of all, there's no marker on this function. If you're using coroutines in a different language, you may expect something like an async in front of the function because we need a marker for this being a coroutine type. That's not happening in C++. So being a coroutine is an implementation detail, which has an interesting effect. If I show you a declaration and ask you, is this a coroutine? You have no way of answering that. It could be one, and in this case it isn't. It's just calling another thing that's obviously a coroutine. Notice something else. We have this function func. It returns an object of type coroutine, whatever that is. We are never actually constructing an object of that type. We are just using the co-return keyword. So this is the first time we have a dissonance between what's in the body and what's on the function declaration, because we don't create the coroutine object, but obviously there must be one created at some point there. And as we'll see shortly, this return type is of utmost importance, because not only does it prevent us to do return type deduction, it also controls what is actually valid inside the body of this function. So these three keywords can actually be controlled by the implementer of that type. And if we were talking about C++20, that's pretty much where we will end right now, because we standardize the facility and no user-facing library. In 23, we get one library type, which is generator. Models and input range, it's lazy. Its body of the function is executed whenever we interact with the iterator. We can use it like this. We can yield multiple times, and we can do a co-return. Notice a co-return can't produce a value. You can only use co-return semicolon. You can, for example, do co-return 6 there. We can't use the co-await keyword at all in a generator. And we use a yield to produce the next element of the generator. There's one more thing. We can use this thing called ranges elements of to yield a complete range, which means the generator will yield all the elements of the range. And there's an optimization potential there for certain kinds of ranges, especially if the thing you're yielding is another generator. And that's an exhaustive list of what's possible with coroutines in 23. So I'm normally not talking about stuff that's not already standardized, but I'm taking a guess that in 26 we will get another type. And that's an asynchronous task for senders and receivers. And I'm not going to talk about senders receivers today. It's a type-erased sender, and it's not actually something you can interact directly with. You need to pass it to a scheduler, which I do here by doing sync wait on the task object. It's a task, so we are returning the result of our task's computation by co-return. And we can co-await on another task, or more specifically another sender or an awaitable. And if you think about it, co-yield doesn't really make sense for a task. But what if I want to use this task in an environment where I'm not allowed to throw an exception? That's something that's actually possible with senders and receivers. And task kind of abuses the co-yield keyword for this contraption that we are not going to talk about in detail, where you can say, I'm going to yield an error code, and it's not actually a yield by the rules of task, because it's doing a cancellation instead. So even though normally if you see a yield you expect to be resumed, that's never going to happen after co-yield with error. Yeah, that's all it in 26. But even then, there's some stuff we need to talk about, which is all the things you need to be aware of when you're actually using coroutines as a user. And let's talk about keywords first. And let's start with this code. I have a branch. In one branch, I do a co-return. In the other, I'm returning what another function returns. Probably the other function is a coroutine. Does this work? Well, the compiler will tell you this is not allowed, which kind of makes sense. You can't at runtime decide whether something is a function or a co-return. Sure, okay, I can live with that. But if I do it at compile time, if you look at this, you'd probably expect this to work, right? The compiler will see either of these branches. In one, it's a coroutine, in the other, it's not. And if you're looking at how the conditional compilation through if const explorer works, you'd expect it to work. But there's an explicit rule in there that tells you even if that return is discarded, it's not allowed to be used in a co-return. Hannah actually thought about writing a paper, but I thought there's been implemented concern about that. So yeah. Not a keyword, no except. I know Danielle will tell you not to use no except. I'll get there. But there's a different reason than the ones she will present you with. So let's think about this no except there. A coroutine needs a coroutine frame. That's probably something that needs to be allocated dynamically on the heap. What would happen if that allocation failed? Well, we will terminate, right? Because we hit the no except. So no except on a coroutine is not a good idea. There's something else hidden in there though. So normally if we see a function and it's marked no except, and we see a throw in there, we know that's a guaranteed terminate because you can't throw from a no except function. This coroutine function can still throw because that no except does not actually apply to anything but the construction of the coroutine frame. Yeah, don't use no except in coroutines. Something similar would happen with contracts, so that also wouldn't work the way you'd expect it to work there. So one last keyword, thread local. We have a thread local variable. We take a reference to that variable. We yield. Sometimes later we come back. Is that assertion that holding? Right, it depends. Coroutines are not bound to a thread. So if you resume in the thread you've been on, everything's fine. It's not a good idea, but this assertion will hold. But there's no guarantee at all that the coroutine won't be resumed on another thread. That example hides something deeper, though. Think about synchronization primitives like a mutex. Holding a mutex across the suspension point is a very bad idea because you need to unlock it on the thread you've locked it on, and you have no guarantee in the code that that will happen. So yeah, that's it for keywords. Parameters. When I started learning C++, I learned if I just need to read an input, I'll take it by const reference. Mind you, we only had L-value references back then. So is this fine? No, not necessarily. It could be fine, but in general, this coroutine will be suspended, and if it's later resumed, we may no longer have that object we are referencing there. So yeah, that may dangle. The general recommendation when using coroutines is to pass arguments by value unless you're really sure that you figured out the lifetime. So passing by value, that's okay. X will be moved to the coroutine frame. It will live as long as the coroutine lives. Unless X is of a type of one of our ever-increasing list of reference-like semantic types, like string view and span. So yeah, combining those with coroutines is dangerous, as is reference in general. So variadics. Oh, C-star variadics. Nobody likes those. Neither do the designers of coroutines. They are not supported. That's a good idea. C++ style variadics. Well, those obviously work. Same rules apply like for anything else you pass per value. If it's of reference type, be aware what you're doing. Okay, one thing that comes up very often when talking about coroutines is, okay, I want to combine coroutines and lambdas. Let's say you have this function, I create the immediately invoked lambda. I'm doing a reference capture. But I've been a good boy, I take the argument by value, so everything's fine, right? No. X is guaranteed to dangle in this case because we are returning whatever the coroutine object is, and we are referencing something that was taken by value. That doesn't help us at all. What did we learn about lambdas when we learned about capturing? If capturing the reference is dangling, we capture by value and everything will be fine. Is it? That one's tricky. You kind of need to do the transformation that happens with a lambda to the struct with the member inside. And then you have to think about coroutines only being function-like entities and not objects. So that's guaranteed to dangle still. That's unfortunate. So how do we do this? So the recommendation normally is to do it like this. Pretend there is no capturing if you need to create a coroutine object locally, and pass in all the stuff you want in the coroutine via the argument list, which means the same rules apply as for normal functions. So that's safe. Everything's okay here. It's a bit wordy, but it works. There's one different way to do this, which is so clever that Titus Winters would probably tell you it's a bad idea. Since C++ 23, we have this thing where we can decide how this object is actually passed to us. And we can just pass the object by value to us, and ignoring the overhead of potentially doing multiple copies there, this is totally fine. I wouldn't recommend this because it's way too clever. Let's talk about something completely different. Let's talk about resource management. We have this pretty simple function. We open a file, we iterate its content, we yield every character we find in it, and at some point we close the file. Is this okay? No. You're right, that's not okay. We may never reach that close. That's a hidden leak. Why is this a hidden leak? Well, there's no guarantee that your coroutine will ever be resumed. So you may be suspended after the first yield, and the user figured out he knows about what's in the file because he was looking for some prefix magic number, and there's no need to carry on. In that case, fclose is never reached, and we have a leak. Thankfully, we can just use IO streams to fix this, because if we are using a resource holder, we can just say, well, this object, this IO stream, will be destroyed either when we reach the end of this function or when the coroutine frame will be destroyed. So that's all you need to be aware of when you're using coroutines. Which brings us to the second part of this talk. How do I actually write a custom coroutine type? And I'm normally not talking about the domains I'm working in because they're not relevant for the talks. But given that we only had a very narrow slice of applications ever using coroutines presented, I think I should go a bit deeper. I'm working, among other things, on something that's called a modeling kernel. You can think about this as something like a CAD kernel, but it's more specialized. In there, we have an operation called sweep. It takes a triangle mesh of arbitrary complexity. It takes a path, and we want to figure out what is the resulting mesh of moving the input mesh along this path. So The left image is the input, the arrows are the path, and the right image is the resulting output. And there's one thing that's very interesting here. We can say this runtime is unbounded. We have no idea, given the input size, how complex this is, because you can model a cylinder, something very trivial with 1 million triangles, or you can have a very complex mesh. And the shape of this mesh will have tremendous amounts of impact on the runtime. The same applies to the path. So this can easily take minutes, and it's more like it can take hours for the wrong inputs. So if you have something that's running on an interactive machine, and it can take minutes to hours, it may be a good idea to provide a way to cancel this operation, because the user may have figured out, well, my input is incorrect, I don't need this anymore. Or, you know what, we've decided this whole simulation needs to be overhauled in any way, so we don't want to do this anymore. So how do we implement cancellation? Well, given this interface, we pretty much have only one way to do this, which is we'll pass something like a callback. There are many different ways we can do this. A function, some stop token, some other custom types. All of them, no matter which one we choose, have severe drawbacks. One of them is we need to do manual checking. And to be able to do checking, we actually need to pass this callback to every internal function, because every internal function can be as well unbounded in time. So that's bad. But it gets worse. If we want to cancel, we pretty much have either to throw an exception, which abuses the idea of an exception being something to signal an error, but the alternative will be to do manual return type checking. So that's probably even worse from my point of view, so neither of these options is great, but yeah. What got me started on coroutines is pretty much one idea I had at one night session, which was, if I would wrap this operation in a task, not execution task, some custom task type, I could do manual suspension checking, sure. I could also do automatic suspension checking at several points in my code. Cancellation is trivial. I just suspend the coroutine and throw away the object, and everything will be freed. No need to do any manual handling of this. And what's not on the slide, I can propagate this logic of how to suspend and whether we need to suspend transparently, not via the function call arguments. So designing a custom type always means we should think about how do we use this, which is especially hard for coroutine types because they have these two interfaces, the one we are using externally without the co-keywords, and the one internally that's using our co-keywords. Let's talk about external usage first. Well, get this task object, and I want to be able to say, I'll wait for so many seconds. If it's not done at that point, well, I'm going to do something different, and in this case, I'm going to continue until at some point I get my result. Then I'm going to use my result. What internally I want to support is, I want to be able to wait for another task, which means that should propagate all the cancellation logic, obviously. I want to be able to throw an exception from here. And I will also probably need something like a generator, and it can't be the std generator because that doesn't know about my cancellation logic. I want to be able to process that with a loop that's also doing suspending. And at some point I want to do manual checking because I know that that code fragment is very complicated. And I want to do this with co-yield and some tag object that's just constructed somewhere in a global header. I don't have modules, unfortunately, right now. And at some point, I want to be able to await another internal task and return the result of that to my caller. So that's the two sides of the task that need to be supported. The question is, how can we do that? And to do that, we need to figure out what the compiler actually does when we have a coroutine. So let's say we have written a function with at least one co-statement. And we have this no except because we want to see that what's going to happen there, not because it's a good idea. Notice the dot dot dots means it's conditional, so it's not as bad as it could be. So the first thing we do when we encounter this is we're going to take the declaration the user gave us and fit in a new definition of this function. Step one there is we figure out what are our argument types. And then we need this thing called the promise. And the promise is a customization point where we can control how the machinery that's going to happen now can be customized. After we've got these two things, we can construct the coroutine frame. And yeah, notice customizable. There's more going on than just a call to the global new. We are not going to talk about that. And then we are going to force move all your inputs into the coroutine frame. That's not a normal move because we need to support people who, for some reason, take arguments by const value. And we don't want another copy to happen there. We want to move these things. So we are doing a const cast and then move here. If you passed in a reference, we are still only propagating a reference. So this is where all this dangling stuff happens. And after we've done that, we need to construct the actual promise. And you are allowed to inspect the arguments that have been stored into the frame if you have a constructor that supports that. Otherwise, your promise must be default constructible. One of these two must work. Once we have done that, it's time to actually start the coroutine. So this will run our body. Notice our body is not here anymore. Our body is somewhere completely different. And once we actually come to the point where we return something to the user, we call promise for the first time and call getReturnObject, which is responsible for producing something we can use to construct a coroutine object. But what happened to our body? So, step 2 of the transformation is we need to figure out what happens to our body. So first things first, we wrap our coroutine body in a try-catch block. And we got this try-catch block by using twice-as bandwidth, which you can read as, this is a conditional suspension point, and the width is to indicate the promises return for initial suspend or final suspend will tell you whether we're actually suspending here. So notice there's also this label final suspend that will be important later on. So if there ever happens an exception, we call unhandled exception, and that is responsible for handling that however it sees fit. If we ever pass beyond final suspend, we are at the point where we know the current coroutine is done. It's run to its completion, there's nothing more to do, so we'll do a self-destruct. That's also customizable. So, oh yeah, we are calling this function multiple times, and we need to figure out where we left off. And we can't actually express that go to where we left off in normal C++. So I'm using a GCC extension that allows us to take the address of a label here, to jump there. Which leaves us with one last thing. Our coroutine body still has all these co-keywords. We need to get rid of those. How do we get rid of those? Well, we turn a co-return with an optional expression into the following thing. We check, is this expression of type void or is it empty? In this case, we call promise return void. Else we call promise return value and pass on the expression we got. Afterwards, we jump to this final suspend because we are done with this coroutine. And the compiler will check that only one of these two functions is there for unknown reasons. There's actually now a paper to get rid of those two static asserts, so we'll see what happens there. So what happens to co-await? Well, co-await is a conditional suspension point. We are using either the expression the user gave us, or if our promise has a member await transform, we're going to stuff that expression in there. Which brings us to yield. And yield is, funnily enough, the trivialest of these. It's just a conditional suspension point going through yield value. So, armed with that knowledge, we can actually, for the first time, implement our custom coroutine type. We can do a simple task. Our simple task must have a promise type. I'm inheriting here from optional because slide space is very limited, not because it's a good idea. And our type will contain something called a coroutine handle, which you can think of as a pointer to the coroutine frame. This pointer does no lifetime management. We are responsible for doing that. So our coroutine type needs move operations and only move operations. It never really makes sense to have a copyable coroutine type because the coroutine frame is by definition a non-copyable resource. What I'd recommend to add is a function to check whether your thing is actually empty. That adds tremendous value, at least during a development of this thing and testing. I'd leave them in for users to check, just for them to be sure. Well, we're going to need a function to get our result. And notice we can call promise on the coroutine handle to get to the object. And dot value is actually the value of our optional base. So this is how we're going to extract the result. We're doing a wait beforehand because we obviously don't want to get to the result if it's not available. And wait is really trivial. We are having a very simple task here. We are checking, is the handle done? If not, we resume it, which starts the coroutine running again. This task type is so simple we can't implement the functions we actually are interested in, so we'll need to do more work here. But let's get to the promise type. Get return object is simple, and the definition of this function borders on boilerplate because in pretty much all the types I've seen, it's the same definition or variation of the same logic, which is we are a promise object and we want to have a handle to ourselves, and that's provided by the static function. Well, unhandled exception is trivial. We just rethrow the exception. And we want to support co-return with an integer, so we are going to just have a return value that then places this value in ourselves. So that leaves initial suspend and final suspend, and we are just saying we want to suspend here. We can do that by returning an object of type suspend always. And this is the complete code we need to get ourselves running. Obviously, we can't do recursion now, and we can't do manual suspension, but we'll get there. But for that, we need to figure out how does this suspension point actually work. So the first thing we need to do is we need to figure out what is our so-called awaiter. And there's an operator co-await that could be triggered here if it's available. If not, we're just going to use the expression as is. And we can't store this thing on the stack because the stack is potentially going away right now. So we need to store this in the coroutine frame. And then we are going to ask the awaiter, is the thing we are waiting on already available? If not, we need to suspend. If we need to suspend, we need to figure out where to resume, and I'm using the same GCC extension here to get the address of that label there to later jump there again once I return to that function. So we figured out we need to suspend. Now we need to figure out what happens now, which is done by await suspend. And we pass in a handle to our own promise. So the promise produced this awaiter, and later on we're passing ourselves in there to call back to us, which is crazy, but works. And await suspend is kind of magical. It supports up to 3 different return types. The first one, which is void, will just return a suspension. So we are done with this coroutine, we return. This coroutine is done, nothing else happens. It could return a bool. In that case, the bool will tell us whether we actually want to suspend now, or we figured out, no, you know what? We can keep going on now. The last thing is, we could get a coroutine handle to some other coroutine. And we will turn this coroutine handle to our support library. And what will happen is that handle will be executed right after we are done here. Whatever happens after await suspend, at one point we will resume, which means we jump to that label. And then we need to build an expression because await and yield can both return a value. And we are going to make sure our awaiter will be destroyed. Jeff, I wanted to use a scope guard. It doesn't fit on the slide nicely. Yeah. I had it on a previous version of the slide. I really want scope guard in the library, by the way, because I don't want defer. Yeah, we then call the awaiter for its last method, which is await resume. Await resume must conjure up the value we are going to pass to the user. Yeah, it could also be void, obviously. So, yeah. So that's an awaiter. That's the part you needed to know. Now we can do manual suspension. And to do manual suspension, we'll need to have a callback. So we didn't get rid of the callback like I said initially. It's just no longer something that's explicitly used. It's stored in the task. And what we're going to do every time we need to do a wait, we're going to update that suspend object. For in this case, when we are calling wait, we never want to suspend, so we want to keep going on. It could also be we want to have wait for, then we check whether the clock has expired. And then we'll need a yield value, and that needs a custom awaiter. And that awaiter will tell us we are never ready because we need to get back to ourselves. So once again, this self is our own object. We've just returned this awaiter from. And here we're just saying, well, jump back to the promise and call suspend and figure out whether we actually want to suspend or not. And await resume does nothing because the suspension doesn't return anything. You could, for example, during debugging, add something like return whether we actually got suspended or not. So we could now try to implement recursion, but there's one more thing, one final thing we need to know about coroutines, which is what happens when we nest them. And I have these two coroutines, bar and foo, and we'll just start by running bar. Oh yeah, initial suspend and final suspend will just suspend in this example. So, okay, we hit initial suspend, we are back out in main and need to do our loop. And that will call resume. We'll call foo. Foo hits initial suspend, we hit co-await and resuspend. So, two coroutines depending on each other, both suspended. What will happen if we resume? What we hope will happen is, well, bar depends on foo. Obviously, foo should run, which is obviously what's happening right now. That's the tricky part. Coroutines don't stack, not automatically. If you want stack-like behavior, you need to implement that yourself in the promise type. The guideline is use await transform or yield value or either to do a conceptual push. The final suspend is the moment you know your coroutine is done, so you can do a pop now. And resuming must always resume the top of your coroutine stack. Oh yeah, one last thing. Coroutines don't nest on the stack. So right on the right there, you see main. Keep close attention what's going to happen now when we return to this situation with both suspended coroutines. Notice we resumed foo, bar was not on the stack. Foo got off the stack and in its place immediately bar took its place. That's symmetric transfer in action. Then we keep running because there's nothing else suspending us and both coroutines are done. So, stack management. We just need to know a few things. Every coroutine needs to know its parent coroutine, which is the coroutine that's awaiting on it. And the bottom of our implicit stack needs to know the top of the stack to know which one to resume. Notice we're resuming the top of our stack now, no longer the handle we're actually holding. And we'll need a function to get to the bottom of our stack, and obviously you would optimize this in real code. And we'll need final suspend, await suspend to do the actual stack management via custom awaiters. Oh yeah, and we need to handle exceptions. As both coroutines are not on the stack, but only the top coroutine is on the stack, you can't actually let that one throw its exception, because you'd skip the outer coroutine. To prevent that, we need to store the exception pointer if we are nested, and rethrow that once our parent coroutine is on the stack again. Stack management, the custom awaiters. So when do we need to suspend? Well, if our handle is already done, there's no need to do all this stack management. We can just get its value. Otherwise, we'll push ourselves on the stack. So the coroutine we are waiting on knows it must resume ourselves. And the bottom of the stack's top pointer points to top now. And we could just now return the handle of other, but there could have been arbitrary amounts of work going on since we last checked for suspension, so it may not be a good idea to check for automatic suspension. And we already got the root, so we can just call this callback. No-up coroutine is a helper function from the library that returns a coroutine handle that does nothing. So we return this handle, the framework would resume it, nothing happens, it gets suspended immediately, nothing happens. Or it's even an optimized version inside the library. At some later point, the pop awaiter will be called, which is task other is now going to be destroyed soon. So the awaiter says it's never ready because we need to do some stack management. So what we're going to do is we pop ourselves from the stack and make sure the stack points to our parent again. We are checking for suspension. If we don't suspend, we return our parent, which jumps back to that await resume of the push await that we created some time ago. We're going to check now, has there been an exception we need to rethrow? If not, we are getting the result of the task and are done. Final question, what happens in that await resume over there? Well, that's unreachable. Nobody will call this function. We could leave it empty. If we're paranoid, we can put an unreachable in there. It will never be called. In fact, our task object will be destroyed right after this return. And with that, I'm at some closing thoughts. So I've implemented this task and generator types. They can await on each other. I've done extensive memory optimizations. A task needs like a pointer size for additional data in addition to the result. A I've implemented allocator support. So if you want to know how allocators work, that may be a good idea to start there. And while doing all this, I figured out there's some work to do for 29 potentially. First of all, I've said it would be a good idea to have this valueless, and we have some types in the library who already have a valueless. For example, valueless by exception of invariant and valueless after move for a new indirect and polymorphic. It may be a good idea to add this to all our coroutine types. I figured out doing it for generator is really hard given that we have existing implementations. And I haven't figured out a way to do it in every implementation until now without breaking ABI. But the more I think about this topic, I think this may be something that should probably be a library policy that makes it possible for us to check whether this object is in a state we can never use it again for anything. Oh yeah, and for reasons that I'm not going to elaborate now, we got rid of 4-core weight in 26 integration of the C++ coroutine design, and I think it's time to rethink whether we can resurrect this. Using asynchronous generators without 4-core weight is doable. The code isn't nice. Essentially, you're down back to iterators, and who wants to use iterators if you can use a 4-core weight? And with that, I'm done.
I was waiting for you.
Thank you for your talk. Thanks. I've got a question about S2 generator.
Yeah.
Because I write protocol libraries, and a lot of times in protocol libraries you get like machine states, state machines. So you get, if you're writing pre-C++ 20 code, you get a bunch of switch cases, or you can use a SIO coroutine, which is a bunch of macros wrapping switch cases. And I was like, okay, we got S2 generator. This is my chance to get rid of all this shit. But then I read the MSVC blog that told that they had implemented an S2 generator, and on the last line they say like, oh, but this is 3 times slower. I was a bit let down by that. So my question is there any, I know about of Halo, and I know about that you might get an optimization, but unless that's guaranteed, at least I don't think I'm going to use it. So my question is like, are there any progress on this kind of guarantee?
Gabby, I mean, I could only answer this as a user, and as Gabby is here, I would pass this on to him.
Unexpected, but yes, I'll answer. I have to acknowledge that the MSVC implementation optimization for coroutine is not as performant as it could be, for example, compared to LLVM. My dear friend Gore, who did implementation for MSVC and LLVM, would agree. I will say keep bringing this up to implementers. Yes, I'm one of those, and you're right doing that. But I'll really encourage you to keep advocating, pushing for implementers to improve the quality of the implementation they have.
Thank you.
I mean, thank you, and that's great, but I was more thinking on something like this kind of guaranteed return value optimization that the standard guarantees, if this could be possible at some point.
Sorry. Okay, so if you're looking for guarantees in the standard itself, then the answer is no. And the reason why it is no is you'll have to go back to 2018-19 and read carefully the whole debate between, the two camps, and why at some point the committee realized that if you want to provide that guarantee, you'll need to invent new laws of physics. And that is a research topic. So what you get now is best efforts, no guarantee.
Okay, you may go on discussing this during the coffee break. Other question?
Yeah. Hi, Michael. Thanks for bringing up coroutines on this talk, and maybe a question in a similar vein. So I was reading the original studio execution proposal. I know that you mentioned that you're not going to bring up senders and receivers, but still, like, it's better to touch upon this topic. And it's in the prior art section, the authors of this paper, they mention callbacks, futures, and, well, coroutines. And just to quote the proposal, in a suite of generic async algorithms that are expected to be callable from hot code paths, the extra allocations and indirections are a deal breaker. It is for this reason that we consider coroutines a poor choice for a basis of all standard async. So for me, as a, like, I don't really like read standard every day. Maybe that's my bad, but still, yeah. If I'm like facing the new code base that I want to introduce async in, I have two vocabulary types now. Two like I have coroutines, C++ 20 coroutines, and C++ 26 studio execution. And I see this. So does that mean that C++ 20 coroutines are basically, I mean, stillborn or?
No. So that paper argues for a fundamental library how to represent execution. And yes, you probably don't want coroutines as the basic layer, but the authors of the paper in this paper or in an additional paper acknowledge that they expect regular users to use coroutines as the user-facing APIs for senders and receivers, which is the motivation for task. So yes, the standard says the paper says we don't want the library that represents all kinds of execution, including pass this onto a GPU to be based on coroutines. That doesn't preclude you from using coroutines at the surface level where that one allocation is by far not the problem they are talking about. They are talking about the accumulation of additional indirections and allocations that would happen if all your frameworks depend on coroutines. And having said that, there's a recent paper regarding networking that actually argues for going in that direction for domain-specific reasons I can't conjure up right now. So it's more complicated than this is stillborn, don't use this. It's use it where it's appropriate.
All right, next question. I got a couple parse errors during the presentation.
Sure.
Like you had a 4-core weight, and you clarified on the last slide that something that was ripped out and might come in again, so that clarifies this. I guess match expressions are not in C++ 26?
Right, and they won't work with that syntax. The question is, do you know why?
I have no idea.
There are multiple answers here. So the first of is, even if you could match for a type, like I do here with void, we don't have regular void in the language, so you can't return a void. So that syntax there wouldn't fly like that. Expressing it with regular C++ involves 3 layers of if const expr with complex checks. That wouldn't help this slide. The other thing that's on this slide that's not working is look at coroutine handle there right now. A wait suspend can return a coroutine handle of any type, not of a specific type, and we can't express this in the language either. I mean, you could leave out this question mark which are borrowed from Java to express that, to say it's a type erased handle, but that's not actually what's going to happen because you're not required to return a type erased handle. You can return any instantiation of a coroutine handle.
Yeah, so sorry that drifted up a bit. My question actually now goes into, I've seen early in your slides use the co-return inside and immediately invoke Lambda expressions.
Yeah.
And that triggered me for the reason that I thought I can only use coroutine keywords exactly in the coroutine and not in a nested function that's called from the coroutine. So why does the co-return work here? Because that's in the call operator of the Lambda. Why is that legal?
But the call operator for Lambda is just a regular function. An operated, overloaded operator is just a function.
So there's just another coroutine there. And now,
But no,
and f is an
there's
ordinary
only one
function.
coroutine here.
And that's a lambda operator, because f is an ordinary function. Okay, I get it. Thank you.
So I have a tiny comment and a tiny question.
Sure.
My tiny comment is, thank you for giving me another case where I should not be using no except. You expected that. Now, can you go to slide 22?
22, sure.
I think. Well,
Is it a green post?
Yeah. So my question, I think you are expecting this question, is what happens when I evaluate get and I have observed semantics?
What's the state of your task? Is it valueless?
Yeah. So if the precondition fails and I am in with observed semantics.
Yes. The same happens if I wouldn't have written the precondition on there.
So I get a crash.
As you would do right now if I haven't written the precondition, you would crash in wait. Because you're calling handle done followed by handle resume, and either of those is not valid if
my point is, you with that precondition, you are giving me a false sense of safety, and I have undefined behavior.
I disagree on that, but we can talk about this offline.
Let's talk about that over the coffee. Okay? You have 30 seconds.
So regarding the coroutine as a basis for asynchronous stuff and senders and receivers, another aspect is that senders and receivers in terms of expressive power are more expressive than asymmetric stackless coroutines, which is what we have. So it's really, if you, for example, here, when we added the third channel, the cancellation channel, we had to go through a hack through the yield. Yeah.
Your 30 seconds are over. Coffee.